The universe we see is only half the story. There should have been another side, an invisible mirror twin, but it vanished. This is the profound mystery of antimatter, and why its disappearance could be the key to unlocking everything we know about existence. In the very beginning, there was only pure energy. A tiny, infinitely dense point exploded outwards, the Big Bang. And in that universe-birthing moment, the fundamental laws of physics tell us something incredible. Matter and antimatter were born in perfectly equal amounts. For every particle of matter, there was a twin particle of antimatter. They are precise twins, identical in mass, identical in properties, but with one crucial difference: an opposite electric charge. And when these opposites meet, something remarkable, yet terrifying, happens. They annihilate each other, disappearing instantly in a burst of pure energy, leaving nothing but light behind. But here's the ultimate paradox, the cosmic riddle. If they were created equally, where is all the antimatter? Why is everything around us, the stars, the planets, the very atoms of your body, made almost entirely of matter? Why do you and I even exist? Let's make it simple. Take an electron, a fundamental particle with a negative electric charge. Its antiparticle, the positron, is its identical twin in every way. Same mass, same spin, but with a positive charge. And here's the rule of the universe. Every single particle in nature has an antimatter version. Protons have antiprotons. Neutrons have antineutrons. When these opposites collide, they don't just disappear, they vanish in a flash, releasing powerful bursts of energy, often as gamma rays. This isn't science fiction. Antimatter is very real. We've not only created it, but we've also studied it in huge laboratories like CERN in Switzerland. In fact, we even use positrons, the anti-electrons, in medical imaging for things like PET scans, helping doctors see inside the human body. So, antimatter definitely exists. But here's the catch. It doesn't exist in the vast amounts our theories expected to find in the universe today. And that's the problem. If matter and antimatter were truly created in perfectly equal quantities at the Big Bang, they should have completely wiped each other out almost instantly. The universe, as we know it, should be nothing but a vast, empty expanse filled with light. No galaxies, no stars, no planets, and certainly no people. But that clearly didn't happen. Instead, there was an almost impossibly tiny imbalance, a monumental 1 in a billion difference. Imagine, for every billion particles of antimatter, there were 1,000,001 particles of matter, all the antimatter annihilated with its partner, releasing energy. But that one extra matter particle per billion, that's what survived. That's what forms everything we see today. That seemingly insignificant imbalance is precisely why you're here. But how did such a delicate, yet universe-defining difference occur? To answer that, we need to talk about something fundamental in physics: symmetry. Physics absolutely loves symmetry. For every action, there's an equal and opposite reaction. For every particle, an antiparticle. But our universe somehow broke this perfect balance. Scientists believe that in the universe's earliest moments, there were tiny, minuscule violations in how matter and antimatter behaved. This is known as CP violation. It means the laws of physics, for a fleeting instant, slightly favored matter over antimatter. It was incredibly subtle, almost imperceptible. But it was enough. Enough to tip the cosmic scales, like a gigantic, delicate balance, nudging the universe towards matter. Experiments like those at the Large Hadron Collider, the world's most powerful particle accelerator, are specifically designed to measure these tiny violations. By smashing protons together at near light speed, they recreate conditions similar to the early universe, hoping to uncover more clues. They want to see if these measured imbalances can fully explain why matter ultimately triumphed. Another powerful idea is called baryogenesis. This concept suggests that the early universe underwent specific reactions that actively created more baryons, heavy particles like protons and neutrons, which make up atomic nuclei, than their antimatter counterparts, antibaryons. But here's where it gets complicated. The standard model of particle physics, our best theory of how the universe works, can't fully explain how this could have happened with enough force to create all the matter we see. So, physicists are looking for new physics, theories that go beyond the standard model. Maybe there are entirely new particles we haven't discovered yet, powerful forces that acted only in the very first moments of the universe and then faded away. Could dark matter, that invisible substance pervading the cosmos, have played a role in this cosmic sorting? Or perhaps, hidden in realms we can't perceive, entire regions of the universe exist that are made of antimatter, separated from us by vast, uncrossable voids. The theories are wild, pushing the boundaries of imagination. But serious scientists around the world are chasing every single one of them. So, how do we search for something so elusive, something that vanishes on contact? We use powerful particle accelerators like those at CERN. We smash protons together at nearly the speed of light, recreating those extreme early universe conditions. In those tiny fleeting flashes, we can actually create antimatter. We then meticulously measure its properties, comparing how it behaves, how it decays, how it interacts. Even the tiniest, most subtle difference between a particle and its antiparticle could be the crucial clue we need to solve the cosmic riddle. We also scan the cosmos itself. We look for gamma rays, those energetic bursts of light, because they are the unmistakable signature left behind when matter and antimatter annihilate. If there were huge clouds of antimatter, or even entire stars or galaxies made of it, we would detect these powerful gamma ray signals as they came into contact with regular matter in the vast interstellar medium. But so far, a profound, eerie silence. No confirmed stars made of antimatter, no galaxies that glow with inverse particles. The question remains, why? What if, against all odds, we were to find an entire galaxy made of antimatter? It would change everything we understand about the universe, about its origins, and about our own place in the cosmos. Imagine, for a terrifying moment, a spaceship made of antimatter accidentally colliding with Earth. Both would instantly vanish in a blinding, inconceivable burst of pure energy, far beyond any nuclear explosion. That incredible destructive power also makes antimatter a tantalizing dream for future energy. Just 1 single gram of antimatter colliding with 1 gram of matter could power a major city for years. It is, by far, the most energy-dense fuel known in the universe. But for now, making even tiny amounts of antimatter is incredibly expensive, and storing it is notoriously difficult and unstable. Still, the research continues, driven by curiosity and the immense potential. Because understanding antimatter isn't just about physics experiments. It's about understanding the fundamental forces that forged our very own existence. The science of antimatter inevitably leads us to the deepest philosophical questions. Why is there something instead of nothing? Why did matter ultimately win the cosmic lottery? Are we just a lucky mistake, a fortunate byproduct of a tiny cosmic imbalance? Or was this outcome somehow inevitable? Some cutting-edge theories even suggest there might be other universes where antimatter did win. Universes where the fundamental laws of physics are subtly reversed, creating a cosmic mirror. Maybe we are just one side of a vast cosmic coin. Perhaps that mirror universe is still out there, existing in a dimension we cannot perceive, subtly looking back at us, pondering the same profound questions. The matter of antimatter is the story of how we came to be, and to understand it is to understand the universe itself. If you enjoyed this journey into the cosmic riddle, please share it with others who dare to ask the big questions. Because curiosity is not just how science moves forward, it's how humanity truly grows. And maybe one day, together, we'll finally answer the most profound question of all: why is there anything at all?